Oh. Two people, so give people another minute or two, and then I'll get started. Okay, very good. Rose Yvonne, Angela Cervantes, Jose Cortez Vargas, Joey Romero, Craigberg Joseph, Anna Logan Jr., Mike Manal, Kevin McCandless, Robert Ochoa, Jack Almas, Alex Head, Keisha Pritchett, and Ronnie Ramirez. Nope. We're missing a couple of people. Yeah. The number of people in the room and the number of people who are supposed to be here. Numbers make sense. Okay. So, welcome to General Science. So this class has a lecture, which you're in now, and a lab. The lab will be immediately after class on Mondays in the same room. You don't have to go anywhere. So you'll just, well, what we'll do is we'll stay here. We'll start the lab when we finish class. Well, we'll start the lab at the lab time, actually. So tonight, if we finish lecture early, we'll have a break. But there is at least one person who's just making up the lab. But we'll have we have a lecture, we have a lab. We will have a lab most weeks. This week is an exception. Lab this week is for getting to know you meetings. There's a sign I just designated the time for it because we won't have covered enough stuff to do a lab yet. So I designated the time for that. The lecture is 1:45 to 3:15 in this room. Lab is on Mondays from 3:30 to 5, also in this room. And then you also have an SI, a supplementary instruction. The supplementary instruction is where you're going to take quizzes. And it's also going to cover review and additional information. That's with David Hamish. That is on Wednesdays from 3:30 to 4:30 in room 205. And lastly, if you want to find me, my office hours are Monday and Wednesday from 12 to 1:30, so before class. In my office, to get to my office, so you came down this hallway to reach this lab. To get to my office, you keep going until you hit the windows, turn left, and my office is on the left. I'm just around the corner, just out of sight. And that's room 335. So if you continue down the hallway right here, all the way down to the end and to the left, and turn around the corner, you'll see my office. And it's the only office in use of a few offices back there. So, in general, if you can't make it to that time, I should be around this part of the building. I teach all of my classes in this room, and my office is down in this room and, well, the big lab across the hall. So you should be able to find me. I may add some extra times. If so, I'll put them up on Blackboard. So there's a block of time on Thursday that I'm free. So I haven't decided when maybe it's a long time. Maybe? Okay. Probably because it's not. I don't know. So that's unfortunate. You need a scientific calculator to do the exams in this class. You don't actually need all the functions listed here. You can't use your phone on exams. I do have calculators I can learn you for quizzes and exams. So don't panic about it. For homework and stuff, you can use your phone. I don't. You can use Google. I don't care. So questions from the exams are based off material from the textbook and the assigned readings and lectures. So you need to attend class. And then you keep up with the material. You can work with each other on things like homework, though numbers will be randomized on your homework because your homework is going to be online. But I don't have a problem with you working together, but no two people are going to have the same numbers in general. I don't know what's going on with this. So, the assessment for this class. About 60% of your grade will be tests and quizzes. There will be 3 tests. One on each section of material we're covering. And there will be 1 quiz per chapter. There's a schedule on Blackboard and a schedule that I will show you in the slides soon that shows when everything's going to be. There's also homework. Homework is about 30% of your grade. Homework will be primarily online through Cengage's WebAssign process. Process for setting that up is fairly straightforward. I'll go over it. If you're having any trouble with it, just drop by my office. I'm happy to walk you through the process. And then there's participation. So that's going to be mostly attendance. I take attendance. Attendance will count for your grade. If you let me know in advance that you won't be able to make it to class for a reasonable reason, like you're sick or you have a sporting event or anything like that, I will excuse that absence, and that won't count negatively towards your attendance grade. Also, part of the participation is the getting to know you meeting. So there's going to be a getting to know you meeting. This is part of the an initiative the school is doing. So it's a 10-minute meeting. There's a schedule for them that you can sign up here at the end of class with a bunch of times available. The getting to know you meeting is going to be worth 10 points. And then there's the lab. The lab is technically a separate course. So your grade on the lecture and your grade on the lab are separate. The lab has 7 labs, 7 labs at 25 points each. 7 or 8 labs at 25 points each. The way lab is going to work, you're going to do the lab in class and fill out the worksheet and turn it in at the end of class. You should have plenty of time. basically, if you show up to all the labs and do the work, you will pass with a good grade at the lab. So here's the schedule. So this week we'll be covering chapter 1 in the book on, it's like an introduction. We will not have class Monday next week because it's Martin Luther King Day and school's closed. But we will be meeting on Wednesday next week. Then we'll move on to chapter 2. Wednesday next week is when we'll have the chapter 1 quiz. Your first homework will be due Wednesday, I believe Wednesday next week. And then your second homework will be due on that day of the quiz. Both of those are on chapter 1. And here's the rest of it. Here you can see the exam on chapters 1 and 2. You'll have a review before it. In general, we'll start the next chapter before we have quiz or exam to give you a little time to get ready. I try not to make it so you have a quiz immediately after you finish. You'll have some time after you finish a chapter. I mean, there's a couple cases where like this is, but I'm not going to give you a quiz the same day you finish a chapter. That would be, so this is the schedule. Spring break. And yeah, this schedule is up on Blackboard in the section called, that's labeled as syllabus and schedule. So you can see it up there at any time. So I do accept late work. Late work will be accepted, but there will be a penalty of up to 15%, generally a 10% penalty. I need to set up the automatic late work thing for the homework. So I just realized I haven't done that yet. But the way I've set it up for the homework is that there will be a button you can press to get an automatic extension if it's past due. And that will give you 2 weeks of extension and a 10% penalty on work you haven't done yet. So if you've gotten most of the homework assignment done and you do an automatic extension, all the work you did before the due date, you get full credit for it. It only penalizes you on stuff you did after the due date. So get as much as you can done before the due date. And so, yeah, if there was something you had trouble with or something you missed, you can always like finish up that last little bit. If you're not going to be able to make it to class, please let me know in advance via email. Then you'll be excused. It won't count against your absences. Now, if you have missed class for whatever reason, let's say you have an excused absence, whatever, all classes are being recorded. So all lectures will be recorded and posted to Blackboard. If you miss a lab, you'll have to do a makeup of the lab. Generally, I set up makeup times for labs at the weeks of tests, and there's a period at the end of the semester for makeups. There's a getting to know you meeting. We're going to have a 10-minute one-on-one meeting to get to know each other sometime in the first 2 weeks of school. There's a sign-up sheet for it up here. So the first period of time that's available is the lab period today, because I don't want to have you do a lab the first week where we barely covered anything, but that's a good time to schedule for getting to know you. If you're here now, you'll be marked present for the lab, so don't panic about that, but sign up for the getting to know you meeting. Sign up for a time slot and make sure to show up to my office at that time, or if it's today, I'm going to be in here. And signing up and attending the meeting is worth 10 points. So it's basically 3 points. Now, homework is going to be on WebAssign. This is Cengage's. It's the textbooks online homework process. The way you do this is you go on Blackboard, you go to the homework section on Blackboard, and then you should be able to click on SCIE102A, General Science, Spring 2025, and that should take you to WebAssign. And it'll offer, if you don't have it, either if you already have a Cengage account from a previous class, you can sign in with that. If you don't have a Cengage account, there's a prompt to make one. But you don't need to look up any codes or anything for this class. You just need to make sure the first time you sign in through Blackboard, because that's how they're tied in. And I can show you how that works. So if I go to Blackboard here, so this is General Science here. And I collapsed this by accident. So see here in the content by type, there is homework. You go to homework. There will be SCIE102A, General Science, Spring 2025. That should be the one that works. If this doesn't work, try this one, the one immediately below it. But if you click here, this should take you to Cengage. Now, for me, it's going to take me to the teacher site on Cengage. But you as a student will see something, once you get this set up, you will see something like this. And there's this getting started with WebAssign for astronomy. And the first homework assignment, SCIE102, chapter 1.1. This is very easy. This is just showing you how the system works. It's a bunch of problems that are demonstrating how WebAssign does like homework stuff. So it's got questions like, this is a multiple choice question. Choose the answer that says this is the correct answer. You know, this is all about just how the systems work, but it will show you how everything works, and so you can get some points. If you go to some assignment, I can't show you you'll see there's a request extension button on the assignment. You can use that to request an extension. And you can either request a manual extension, which I would not suggest, because a manual extension sends me an email and then I have to manually add the extension or deny the extension. And that is slow. If you want it right away, do automatic extensions. So right now they're not turned on because I forgot to do that yet. Because it doesn't copy over. But I will do that immediately after class and make sure that if you're having any trouble getting into this, just stop by my office sometime, stop by after class sometime. I'll help you set it up. Should be straightforward. This is a lot easier than it used to be. It used to be you had to enter in like a code, and it used to be that you would enter in a code that was provided with the textbook and a code for the class, and it was a huge pain in the butt. I will skip that demonstration, and then I'll get started with the actual. Let's see. Oh, this is working now. So this is chapter 1 in your book. Your book is physical science. You should have a physical copy, but you could also access it once you sign in to Cengage. You can also access the ebook. So back on Blackboard, there's a link here for the ebook in the homework section. And you should be able to, for various questions, if you're doing homework for various questions, there should be a way to link to the appropriate section of the book for the question. So any questions about how the classes run, anything like that? Okay. So we're going to start with some of the basics of how science works. We're going to talk about measurement and how we do measurement in such a way that we can share information, all the appropriate information with other people. And we'll talk about how the scientific method works and things like that. And this is acting up. So basically, science is a description leading to understanding of our environment. Science is about asking, okay, how does this thing I see happening in the world work? And making a description of our environment that is effective and can be used to make predictions requires some sort of measurement of the physical world, particularly in the physical sciences, which is primarily what we're going to talk about in this class. Now, understanding our environment requires interpretation of accurate measurements. You need to make good measurements of what's happening, and you need to then interpret them. So understanding measurement is essential to understanding the world because it's how we get information about the world. Now, in the modern day, we've developed extremely sophisticated methods of measurement. We can measure all kinds of stuff to levels of precision that are honestly quite insane. So measurements, we can measure things like movement, temperature, weather conditions, time, etc. You know, you measure electricity, things like that. We're going to use lots of measurements throughout this book. Primarily, the most common things we're going to be measuring are distance, time, and mass, and combinations thereof. But we also will measure temperature and things like that. And we can ask ourselves the question, can we measure everything with certainty? And the actual answer to that is just no. It's actually a fundamental principle that it is impossible to measure anything perfectly. It turns out, as we get smaller to smaller and smaller objects, it is impossible to measure something without affecting it. Basically, it became apparent that the act of measurement, to measure something, you have to interact with it in some way. Now, if I'm going to measure, I mean, for example, if I'm going to measure, if I'm going to see where something is, I have to bounce light off. But that's an interaction with it. And that can cause it to move. So it's not necessarily where I saw it was anymore. That's the general idea. At the smallest levels and at the most detailed levels, it is in fact impossible to measure anything with perfect certainty. There's a sort of trade-off. The better you know one aspect, the less you know some other aspect. So the better you know where like a subatomic particle is, the less you know how it's moving. That's sort of the trade-off. You can know how fast or how something's moving, but if you know that very precisely, very precisely, you don't know where it is as well. So this process of measuring things actually distorts the thing because you have to interact with it in fundamental way. This is what's known as Heisenberg's uncertainty principle. You may have heard of it. We're not going to actually go into the details of that, but just understand that there's in fact a limit to how accurate measurement is. And it's like a fundamental difference. It's not like we should develop a better technique. Now, this is at like the subatomic level. Oh, I thought I had these before. Oh yeah, I think it's that one. So, sorry. I thought I had a quick flash. Nope. So I will pull it up. That's the one. Scales of various objects. The sound settings are wrong. Now it's way. So, physical science is a subset of the natural sciences. The natural sciences are physical science and biological science. And the physical sciences are things like physics, chemistry, geology, meteorology, and astronomy. Generally dealing with stuff, sort of more basic stuff, and not dealing with living things. So we're going to talk about the fundamentals of this book covers the 5 physical sciences. This class will be covering some fundamentals in physics and chemistry. If you want to do geology, meteorology, and astronomy, that's what the geology course is. So the sciences can be split into the social sciences and the natural sciences. The natural sciences can be split into the physical sciences and the biological sciences. Physical sciences are things like physics, chemistry, astronomy, meteorology, geology. These three are earth and space science, which are covered in a different class. We will be covering physics and chemistry stuff. I admit there's a bias towards physics because I'm a physicist. So the way you investigate things scientifically is really you ask questions and you test those questions. But at some basic level, the way you can test your ideas about what's happening is by making measurements. So what happens is that measurements are sort of the basic core of scientific research and investigation. You go out into the world, you observe things that happen. You ask questions about how or why these things happen. And then you propose a reason how or why these things happen and to figure out a way to test it. So you start by making measurements of what's happening, and then you put together an experiment to test a question. So scientists basically assume the universe is orderly and can be understood. And the idea of measurement is very important because it's a way we can share information with other people. If we can measure things accurately in a way that other people understand, I can write down what happened and they can know what I saw. Now, the scientific method or the general scientific method, which is sort of the general concept and rules of observations, rules for reasoning and making predictions, can be broken down into basically 4 main steps. And you start by making observations or measurements of the world. Then you make a hypothesis. You ask a question about the world, and you propose an answer. And then you test that. You test whether your proposed explanation is true. That is the big scientific revolution that happened in the 1700s. The idea that nothing is considered true unless we can test it based on the real world. We can't just make arguments from pure reason. That's what people used to do for thousands of years. So what we do is we do experiments, we do tests, and we try and prove our hypothesis either false, true, or false. And if a hypothesis holds up to lots of experiments and holds up to lots of tests, it becomes a theory. So scientific theory is a very solid idea that's backed up by experimental evidence. There's also a law. The scientific law is subtly different. So a scientific theory is an explanation of why something happens. A scientific law is a description of something that happens. These days, people don't use laws much anymore. Older things. Well, we will talk about the difference between the two. There's sort of 2 different ways you can have an endpoint, but a law is something that happens, but not an explanation for why. It's like a mathematical description of what happens. Well, theory is an explanation sort of for why. They're sort of a bit fuzzy between them, but you'll notice that people don't make new laws much. So we can start by making observations and taking measurements. You collect information, you collect quantitative data. Quantitative just means stuff with numbers on it, while qualitative means descriptive. The quantitative data is data with numbers. We gather that using the senses along with the assistance of technical instruments. We use technical instruments to overcome the weaknesses of our senses. We can use instruments to make measurements beyond what we could do on our own. So for example, you can use a set of calipers to measure something to more precision than you could measure with a ruler. You can take a photograph instead of drawing a picture of what you see with your eye. And that has the advantage it doesn't pass through your brain, so you don't suffer from various optical illusions or things like that. They could get, because we have these amazing brains that are very good at processing information, and sometimes they're a little too good. So the senses. These are things like sight, hearing, smell, taste, and touch. For humans, sight and hearing provide the most information to our brains about our environment. That's just the way humans work. We are sight-based creatures. And while touch and taste and smell can all be used, so generally taste and smell are not used so often anymore because randomly tasting various concoctions you made in the lab is not usually the greatest idea. We just do it all the time. And then we use instruments to extend our ability to measure beyond the limitations of our senses and learn more about our environment. See things that are smaller than we can see with our eyes, see more details. And our senses can be deceived. So for example, when you look at the sun and other stars in the sky, the sun looks much, much bigger than any of the other stars. All the other stars in the sky look to be about the same size. They're all little points. In actuality, the sun is a middling to small size star. And some of the stars out there in the sky are enormous, huge, even though they all look to be about the same size. It's just because they're so far away. They're all reduced down to points. So a hypothesis is a possible explanation for the observations you made of the world. So an example hypothesis is saying matter consists of small particles, atoms that simply rearrange themselves. That's the hypothesis of the atomic theory. This is a tentative answer or an educated guess. This is the thing you're going to test. If you want to see the scientific method boiled down to its most basic, I know I'm a little dated for using this, but watch Mythbusters. Mythbusters as a show did the basic thing of science. They ask a question and they test it. And sometimes they go back and test it again to see if they maybe screwed up the first time. That's the core of science. You ask a question about something, and then you do a test to see if it's true. This is asking the question. This is proposing an explanation for what you think is happening, and then you test the validity of that by designing experiments. And if your hypothesis correctly predicts your experimental results, then it's good. You have a good explanation. And if it doesn't, then you need to go back and develop a new hypothesis or a new model to explain what's going on. So to test hypotheses, to test your ideas, you do experiments. So this is testing under controlled conditions to see if results support or confirm or deny the hypothesis. Generally, you want to design your experiment so there's some way that your hypothesis can be shown wrong. Actually, kind of an interesting thing. There's a bunch of bias involved. In reality, people aren't perfect. There is scientific bias, things like that. And people make mistakes. So sometimes, you can go back and realize that something that people thought was important had a mistake in the way they set up the experiment. That actually happened in the field I was doing my PhD research in. The first experiment that started the little subfield I was doing got repeated right before I defended my dissertation. with a better designed experiment where they got rid of, there was like an empty gap in the first design of the experiment, and they got rid of that gap. So that gap didn't get filled up with solid helium. And when they did it without that gap, the phenomenon they thought they were seeing went away. And that was a big deal. Killed a bunch of ideas about what that would have done. Luckily, my research was also pointing in that direction. So that was good, but the timing was kind of stressful. So an experiment is sort of a test. You try and control as much as you can. Generally what you have is you have something that you control and something that you measure. And you vary the thing you control, and you see how the thing you measure varies, how the thing you measure changes as you vary the thing you control. And this is a little confusing, but the thing you control, the thing you have control over, is called the independent variable. Because it doesn't depend on anything other than you, the experiment. The independent variable is the variable that you are under control of. It's the slider you're moving back and forth. So the independent variable in an experiment is the factor that's changed by the experiment. This could be time, this could be temperature, this could be lots of things. A dependent variable is something, so independent variable is basically your input. Your dependent variable is your output. It's what you're measuring. You want to see how, if I change temperature, how this other property changes. Like volume. So that would be your dependent variable. This is a factor that's affected by the changes in the independent variable. And then in certain types of experiments, you're dealing with something that's either on or off, kind of, especially for things like testing medicine. So you'll have a control. And a control is something that's used, it's basically a test where you do nothing. And you use that to show that the results you're seeing are caused by the thing you're doing and not happening on their own. So if you have a drug that you want to test if it works, if it cures some disease, you're going to give one group of people the drug and another group of people, you're going to not give the drug. Generally these days you give them like a placebo, fake pill that they think is the drug, to get rid of as many variables as possible. Because it turns out thinking you are receiving medicine can actually have an effect on your health. But like a control is basically, you have one group where you do the thing, and the other group where you don't do the thing. And it's just a way to test that the results you're seeing are caused by the thing you're doing and not something that happens on the own. Now, in something where you vary something continuously, the control is kind of the first data. You don't have to worry about it. So here are some examples of variables in an experiment. The controlled variable here, the independent variable, is time. That's the thing that you're controlling and watching and measuring. And the dependent variable is temperature. So what's being controlled by time is probably the amount of chemicals involved as they're being consumed by the reaction. But your independent variable here is time, and your dependent variable is temperature. And then you can plot this. You usually plot the independent variable on the x-axis and the dependent variable on the y-axis. And that gives you a graph that you can share with other people. So during a scientific experiment, all the data gets carefully recorded. Then you present it to other people. You can use graphs, tables, and charts to display data. Most common thing is graphs, lots of graphs. And then you analyze that data so the conclusion can be drawn. So often what you'll do is you'll have a graph of your data, and you'll have a graph of your prediction, and you'll show that they match up. You'll put them on top of each other and show that they match up. And Ideally, you should set your experiment up so your experimental results can be duplicated by other researchers. There are definitely some problems with that sometimes. When people can't duplicate the results, there's been a lot of issues in people looking for high temperature superconductors and things like that recently. And no concept or model of nature is valid unless it is in agreement with experimental results. So if you have some elaborate theory, you need experiments to back it up. So a theory is a tested explanation for a broad segment of basic natural phenomena. An example of this is atomic theory. Stuff is made of small atoms. These atoms combine and separate in chemistry. And this theory has withstood testing for something like 200 plus years. And depending on continued experimentation, theories can be accepted, modified, or rejected. Often, you'll get in situations where you'll find some extreme situation where your old theory stops working. So you'll develop a new theory that acts like the old theory under normal circumstances, but is different under the extreme circumstances. So an example of this would be general relativity, which handled sort of extremes of gravity and speed. Newton's laws of motion and gravity work just fine under most circumstances, but under extremes, you need to switch to general relativity. So that's sort of a modification, expansion. Now, a scientific law is, after a series of experiments, it's a concise statement, usually words or math, that describes some fundamental relationship of nature. So an example is the law of conservation of mass, which is that during a chemical reaction, there is no gain or loss of mass. The mass you have at the beginning and the mass you have at the end are the same during your chemical reaction. And the law simply states what happens, but it doesn't explain why. Why the mass remains the same is explained by atomic theory, because a chemical reaction is just having atoms change how they're bound to each other, and that doesn't change their mass. Nothing is gained or lost. The same stuff. Okay. I thought I had this as a thing. And here is a short video about theory versus law.
Scientific theory versus scientific law. It is important to understand the similarities and differences between a scientific theory and a scientific law. Both scientific theories and scientific laws describe something that has been observed in nature. They both require many observations and experiments, and they both must be accepted by the majority of the scientific community. However, scientific theories are not laws, and they are not treated the same as laws. Unlike a theory, where evidence changes, a law will never change. In science, a theory is a widely accepted explanation supported by abundant scientific evidence. Theories are not just ideas or guesses about how something works, and theories are not just opinions about a concept. For science to prove a theory, scientists must conduct extensive tests and experiments. A theory must be supported by tremendous amounts of scientific evidence, and it must go through peer review and retesting. Even if a theory is proven, it is subject to change in the light of new evidence. This is the best way for science to evolve and change. In this way, scientists can use theories to build upon the evidence and ideas of other great minds. One good example of a theory that has evolved over time is Newtonian mechanics, first theorized by Isaac Newton in the 1600s. This theory explained the movement of objects, both on Earth and in space. Using Isaac Newton's work, Albert Einstein perfected the theory, renaming it the theory of special relativity. Einstein's new theory put a twist on the Newtonian theory, allowing us to measure objects in reference to space and time. Einstein even upgraded his special relativity theory to a more current version that we use today, the theory of general relativity. Scientific laws are different from scientific theories. A scientific law is a description of a fact that is completely accepted in the scientific community. A scientific law does not change, and if it is refuted, not only does the law become false, but all science that was based on that law also becomes false. Laws state that something in the natural world happens, but they do not necessarily explain how or why. The law of gravity, for instance, states that all objects have a force of attraction for each other. This law explains what happens, but not how it works or why. Theories attempt to explain the how and why. When trying to decide if something is a scientific law or scientific theory, ask yourself this question: does it explain what happens, or does it explain how and why something happens? If it explains what happens, you are talking about a law. If it explains how or why something happens, you are talking about a theory.
So that's the difference between a theory and a law. And the scientific method is basically a cycle. Make observations and measurements. These lead to hypotheses. We do experiments to test these hypotheses. These form theories, which lead to you making more observations and measurements and developing new hypotheses, new theories, building up. Now, in order to share information with other people, we use units. These are standardized measurements that allow us to share things between other people. They're agreed conventions about measurement. And systems of units have been around for a very long time. They were originally developed for, well, a couple things: commerce and taxation. Boils down to money. People developed units so that you could measure how much you owe the government, or you could know how much you're getting when you're buying something. So there's some sort of standardized measure for purchases or trade or things like that. And measurements are expressed with a magnitude, that's just a number, and a unit. So you have, say, if you're measuring a distance, it could be like 3 centimeters. If you're measuring time, it could be 30 seconds. Magnitude is the number, the unit is the unit. In general, you need both of those to have the correct answer on things. You will lose points if you don't put them on your answers in tests and quizzes. Now, the study of force and motion requires actually only 3 basic units and things derived from them. And the standard unit is the standard agreed on fixed reproducible value that we use to take accurate measurements. And the world we live in uses the SI system, or the International System of Units, with 7 base units that all units we use are based on. These are the metric units, the metric system. And while we live in America and we use other units, the definition of all those units is actually just a number of metric units. So like a pound is so many kilograms. That's how it's defined. Things like that. So there's 2 main systems of units. There's the British or English system is the term for it. Technically, the official term is US customary units. That is the formal term for that the system of units that's used in the US. This is only used widely in the US. Now, a few of them hang around in other former British colonies, or Britain itself, but these are things like miles, inches, pounds. Time is also seconds. Seconds is the same in both systems. And basically, we're the only country in the world who primarily use it. And then there's the metric system, which is used throughout most of the world. We measure distance, big distances in kilometers, meters, masses in grams or kilograms, and so on. And the US actually officially adopted the metric system back in 1893. We kind of suck at actually transferring over. The reason why is people don't want to change, and we can afford to use a weird mixture of units because we're wealthy enough for that. But yeah, it's basically turns out to be certain people would have to spend a whole lot of money to change over all their tools. And they push strongly against it. And then just in general, the US never tried very well. So length. Length is the measurement of space in any direction. It's what you measure with a ruler. Here is the base unit of length, a meter. This is a meter stick. The metric standard unit is the meter. All the metric units, when they were created, basically during the French Revolution, or a French Revolution, I don't remember which one. France has had a bunch of revolutions. They were defined, they were attempted to be defined based on quantities of nature, because it was supposed to be a more scientific system of units instead of these sort of arbitrary values. So the meter was originally defined as 1/10,000, 10 millionth of the distance from the equator to the North Pole at Paris. The British standard unit is the foot, which is a very old unit based off of the human foot. The unit of a foot has been around since the Roman era. It was a Roman. And there was a Roman mile and things like that. But the meter, originally defined as 1/10 millionth of the distance from the equator to the North Pole. Since then, we've realized that's not a great way to define that, because it turns out, depends where you are on the Earth. The Earth isn't perfectly round, things like that. So that's how it was originally defined as a physical quantity of nature. Well, 1/10 millionth of the distance from the equator to the pole. It's a little bit longer than a yard if you want to reference the units you might know. Now, the modern definition of a meter is based on the speed of light. The meter is the distance traveled by light in a vacuum in 1,299,792,458 of a second. Basically, what we did is we took the meter we measured the speed of light in meters per second very accurately, and then we cut it off to a whole number. And we use that to define the meter. So if you know what a second is, you can use that to figure out what a meter is. And the speed of light, the advantage of the speed of light is that it is a universal constant, the fundamental property of the universe. Speed of light is the same everywhere. It's the speed limit of the universe. So speed of light is 299,792,458 meters per second. Exactly. And all the other units are defined by things like that. Now, mass was the hard one, it turns out. We didn't get a fundamental definition of mass until quite recently. So the amount of mass is a measure of the amount of stuff that's in an object. An object's mass is always constant. All an object's weight is not, because weight is a measure of how strongly gravity is pulling you down. Mass is a measure of how much stuff you are. So if you go somewhere where the gravity is less strong, your weight will be less, but your mass won't change. Which does mean that the easiest way to lose weight is to take an elevator up to the top of a very high building, because gravity is slightly weaker higher up. You will lose a minuscule portion of your weight, and you will get it all back as soon as you come back. The mass is a fundamental unit that remains constant throughout the universe. Our unit for mass, the metric standard unit, is a kilogram. That's 1,000 grams. And it was originally defined as the amount of water in a cube that's 10 centimeters on a side. The problem with that is that the density of water changes with temperature, stuff in the water, and things like that. It's not actually a great measure. And until 2019, and because of that, until 2019, the definition of a kilogram was a cylinder made platinum iridium cylinder in a vault in Paris. That was what defined the kilogram. It was a physical object. And the problem was we knew that its mass was changing because all the copies of it were diverging in mass. So, we measured them all. They were all the same at one point. We measured them all again later, and they vary slightly from each other. Obviously, the kilogram is still that one that is the kilogram, but we know that the copies are changing in mass. This is a bad way to reference this. And so now it's actually based on a fixed value of the Planck constant. Planck's constant is another fundamental measurement, has to do with things like the energy of light, particles, and things like that. But Planck's constant is now fixed to this number, and that is used to define the kilogram. And the process by which they did this was very complex and kind of insane, but really kind of interesting if you want to look up watt balance, that's what it's called. No, it's a Kibble balance, sorry. Sometimes also called a watt balance. So this is the US prototype, number 20 kilogram. This is one of those copies of that cylinder. So basically a cylinder in glass like this was the definition of a kilogram up until 2019. It was only like 5 years ago. And you can see here, it's actually a little bit less than a kilogram because its mass has changed over time. Now, the standard unit for mass in the British system is the slug. Nobody uses this unit. What they use are called mass pounds, which is the mass of 1 pound of something that weighs 1 pound at standard gravitational force. We use the pound, which is actually a measurement of force, not mass. It's a measurement of weight. It's related to gravitational attraction. But there's something called the mass pound, which is what all the engineers use. And a mass pound is a measure of, it's the mass of 1 pound at, standard surface gravity. And the weight of an object varies slightly depending on where it is on Earth. For example, at higher altitude, it's less. If you go towards the equator, it varies with your latitude. So if you travel south, I think your weight will go up. Oh, no, it goes down. But yeah, it varies with latitude as well. But mass is a fundamental quantity. It remains constant while weight varies. So if you weigh 300 pounds on Earth and you go to the moon, you'll weigh only 50 pounds because gravity on the moon is about 1/6 of gravity on Earth. Now, time is the continuous forward flowing of events. Time only goes forward. Don't ask me why. That is one of the deep unsolved questions that no progress has been made on. The unit for time, and the standard unit for time in both the metric and British systems is the second. And the second was originally based on a day. Now there are 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. The subdividing things into minutes and seconds was originally something done for degrees and angles, and it was later applied to time. And the word second actually comes from, means literally second division. Because minute comes from like minuta for division. And then when we did it again, it's second minuta. So it actually comes from second, as in the second thing, after the first thing. But it was originally 1/86,400th of a solar day. The problem there is that the rotation of the Earth is changing over time. Earth is slowly slowing down over time. There's some variation, various things. So for example, when they filled the Three Gorges Dam in China, that changed the rotation of the Earth. So you have to correct for that. So now the second is defined based on the vibrations of a cesium-133 atom. So for cesium-133, so originally a second defined, I didn't think a second is defined. It's a fraction of a day. 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, which is 1/86,400th of a day. But because a day isn't actually completely consistent, now it's defined by the hyperfine transition of a cesium-133 atom. So if you get some cesium-133 atoms and you excite their hyperfine transition, I believe it's the hyperfine transition, and you count the oscillations you get, and you do this basically by hitting it with radio waves. You hit it with light and watch the light bounce, and it generates radio waves as it oscillates. And then you just count the oscillations. And when you have 9,192,631,770 oscillations, that's 1 second. There are actually people working on even finer, faster oscillating things to measure time, even to finer gradations. Because apparently 9 billionth of a second isn't fast enough for people. But that is the current definition. You look at the vibrations of this specific atom in this specific transition. And all cesium-133 atoms are identical, so anybody can find a cesium-133 atom and oscillate. Now the metric system, the stuff we actually uses what's uses the acronym MKS, the MKS system, from the standard units of length, mass, and time. This is because there was another related system that people used to use that was called CGS, that was developed on slightly different principles. It used to be popular, nobody really uses it anymore these days. But that's why it's called MKS. It's a decimal, it's a base 10 system. This is much more convenient than the weird mixture of transitions that is in the British system. The reason the British system is confusing like that is because it's actually a merger of several old systems into one, and they combine very strangely. And it's administered by the Bureau International des Poids et Mesures, the BIPM in Paris. That's the International Bureau of Weights and Measures. And it's the International System of Units, which is abbreviated SI, because in French, it is System International. They put the adjectives in a different location. And there are 7 basic units. We've talked about 3, mass, distance, mass, and time. Those 3, the meter, kilogram, and second. Those are length, mass, and time. And then there are 4 more fundamental units. There's the ampere, which measures electrical current. And the reason they use electrical current and not electrical charge is because historically it was a lot easier to measure electrical current. There's Kelvin, which is temperature. Kelvin is like Celsius. You may have heard of Celsius temperature or centigrade temperature. But instead of starting at the freezing point of water, which is where Celsius starts at, the Kelvin temperature scale starts at absolute 0, the coldest temperature that you can have. So all Kelvin temperatures are positive, and they correspond more fundamentally to the fundamental idea of what temperature is. You don't have negative temperatures or anything like that. Then there's the mole, which is a way to measure amount of a substance, how many atoms you have by weighing things, the relationship between weight and atom count. And lastly, there's the candela, which is a measure of luminous intensity, which is a measure of how bright things are, how much. Now, the nice thing about the metric system is that you have those standard base units, and then you have a set of prefixes or modifiers that you apply. And it's always the same prefixes for all units. This makes conversion, and all the prefixes correspond to powers of 10. So conversion is relatively straightforward because multiplying by a power of 10 just means moving the decimal point. You don't actually have to do any calculations. You just need to move the decimal point. So 1 kilometer is 1,000 meters, while 1 mile is 5,280 feet. 1 meter is 100 centimeters, while 1 yard is 3 feet or 36 inches. 1 liter is 1,000 milliliters, while 1 quart is 32 ounces or 2 pints, and a gallon is 128 ounces. Actually, the volume measurements in the British system aren't too bad because they're all powers of 2, but yeah. So we'll go through all the prefixes eventually, but here are some commonly used prefixes that you're going to use in class. So mega means 1,000,000. So you may have used this before, like a megabyte. A megabyte is 1,000,000 bytes. That's 10 to the 6th. You can see there's 6 zeros in 1,000,000. Another common one, kilo, kilogram, kilometer. Kiloton. That's 1,000 times the base unit. Kilobyte. Maybe use these in computing. The big numbers, the big prefixes get used in computing a lot. Then we can go to the small ones. We have centi. Centi is 100. So centimeter, centiliter, centigram. The most common one you're going to run into is centimeter. Milli is 1,000. Millimeter, millisecond, milligram. There's a complete listing on page 13 in your book, I believe. But we will go through these. So again, the 3 units, mass, length is the meter, mass is kilograms or grams, time is seconds. Volume will be things like cubic meters or cubic centimeters. So you can have derived units, units that are made by combining existing units. So volume is, for example, meters times meters times meters, because volume has got length, height, and width. So you have cubic meter or cubic centimeter. And here is a more complete list of the prefixes. So for big, you have kilo, that's 1,000. Mega, that's 1,000,000. Giga, that's 1,000,000,000. That's 10 to the 9. The next one is tera, and then the one after that is penta. Now, going for smaller numbers, a tenth is deci. Sometimes decimeter gets used. Deciliter gets used. Shows up every once in a while. Not that. Centi is very common. It's 100th. Centimeter, centiliter. Then when we get to the set, so there's like a 10 and 100, and then it's by powers of 1,000. You see how it goes 10 to the third, 10 to the sixth, 10 to the 9, 10 to the 12. Here it's 10 to the third, 10 to the sixth, 10 to the 9. We skip the 10 and 100 for the bigger. They exist, but we don't use very often. Milli, millimeter, millisecond, milligram. Micro, notice how this is the Greek letter mu. It looks like a U with a line on the front. If you're typing it out, you can often type just a U, but this is the proper way you write it. Micro is a millionth, 10 to the minus 6. Nano, you may have heard of nanotechnology. That's technology on the scale of nanometers. So nanometers, nanoseconds, nanograms, that's 10 to the minus 9. You might see micrograms or nanograms in medicine. Amount of medicine in like a pill. And then we have pico. Pico gets used for picometers for when you're measuring like parts of an atom. Picoseconds sometimes get used for time. That's a trillion. 10 to the minus 12. So 10 to the minus 1 times 10 to the minus 3 meters, you could write that as 1 millimeter and not have to write, 1.001 meters. You can just write 1 millimeter. So by switching to these things with prefixes, it makes it a lot easier. So a non-standard metric unit that we use is the liter. It's a measure of volume. Probably have a decent idea of what a liter is because of 2-liter bottles. 2-liter bottles hold 2 liters of liquid. Probably may have also seen 3-liter or 1-liter bottles, things like that. A liter is the volume of liquid in a 10 centimeter square, cube. It's 10 centimeters by 10 centimeters by 10 centimeters, 1,000 cubic centimeters. So it turns out that 1,000th of a liter, a milliliter, is the same size as 1 cubic centimeter, which makes converting between cubic centimeters and liters pretty easy. And also, for water, weighs 1 gram. A liter of pure water has a mass of 1 kilogram, or 1,000 grams. So 1 cubic centimeter of water has a mass of 1 gram, and a volume, is also 1 milliliter. So 1 milliliter equals 1 cubic centimeter, which equals 1 gram of pure water. So 1 milliliter always equals 1 cubic centimeter. Those are always the same size, but only for water will it weigh it. But if you have like a kitchen scale, you may have seen a kitchen scale will have options for units. You'll have a unit of 1 milliliters on it if you step through the units. That's because the weight of water is 1 gram per milliliter. It's actually just measuring in grams. So that's the density of water. But if you have other liquids, that's not going to apply. So if you have something that's more dense, like say mercury, a cubic centimeter of mercury will weigh like 13. While a cubic centimeter of alcohol will weigh less. Now a liter is a little bit more than a quart. So it's 1.06 quarts, or 1 quart is about 9.46 liters. And it's the amount of water in a 10 centimeter cube, which will weigh 1 kilogram. Another commonly used unit is the metric ton. It turns out there's a lot of different tons. The metric ton is the mass of 1 cubic meter of water. It is 1,000 kilograms. 1 meter is 100 centimeters. So this is 1,000,000 cubic centimeters. That's 1,000 cubic centimeters is a liter. So 1,000 liters in 1 cubic meter of water. 1 metric ton is actually 1,000 kilograms. This actually puts it a little bit bigger than the standard short ton that is used for in the British units. So in British units, the short ton is 2,000 pounds. A metric ton works out to be about 2,200 pounds. But of course, there's also a long ton because there are many units that have the same name but are actually different, which is around 2,400 pounds. But the metric ton is 1,000 pounds. And that's most of the time when people talk about tons these days, at least in like shipping and official stuff, they're talking metric tons. Now, it's difficult to make all measurements directly with just the 7 fundamental units. Often we need to combine them into derived units. So we've used some derived units like volume. Volume is length cubed. So meters cubed, centimeters cubed. Area. Area is length squared. We measure it in meters squared, feet squared, square meters, square feet. So like your apartment has so many square feet. And then things like speed. Speed is length over time. That's meters per second, miles per hour, etc. Eventually, we'll get to the point where units are complicated enough that we don't just express them as the base units, we give them a name to save ourselves the trouble of writing them out. So, like the unit for energy is kilogram meters squared per second squared. No one wants to write that out. We gave it a name called a joule. We'll get to that when we actually get to it. Now, density is a measure of mass per unit volume. So density is a way, it's mass divided by volume. So it's mass over length cubed. And it's a measure of sort of how compact the substance. Density is a property of a material. So if you cut something into half, its density isn't changed. Typical units for density are grams per cubic centimeter or kilograms per cubic meter. While technically kilograms per cubic meter would be using the standard units, in practice, grams per cubic centimeter are used more often, just because the numbers are nicer. So water has a density of 1 gram per cubic centimeter. When we compare things to water, things like aluminum has a density of 2.7 grams per cubic centimeter. Iron is 7.8 grams per cubic centimeter. Gold is 19.3 grams per cubic centimeter. The average for the whole Earth is around 5.5 grams per cubic centimeter. Turns out if you do it in kilograms per cubic meter, aluminum will be 2,700. It's just more often. So grams per cubic centimeter gets used more often. Also happens to be, for practical purposes, often a lot easier to measure mass in grams and volume in cubic centimeters for smaller objects. Nobody wants to deal with a cubic meter of anything. A cubic meter is really big. Cubic meter is big. So for liquid densities, a common way we measure them is using what's called a hydrometer. This is basically a weighted glass bulb. So it's hollow, but it's got a weight in the bottom, and it floats. And how high it floats corresponds to the density of the liquid. The denser the liquid, the higher up it will float. So pure water has a density of 1 gram per cubic centimeter. Seawater, for example, is more dense. It has a density of 1.025 grams per cubic centimeter. Something like urine can vary from 1.015 to 1.030 grams per cubic centimeter. But things like antifreeze or alcohol are less dense, so your density goes down. So one of the ways these get used, the denser the liquid, the higher the hydrometer floats. These are actually used to measure alcohol content with things. So if you're making like spirits, you just measure the density directly because basically you have a mixture of alcohol and water. If you're making like vodka, whiskey or something. But if you're making like beer, you measure your density before you ferment and then you measure it after. Because you change from higher density sugars to lower density alcohols. And the change lets you calculate how much alcohol is in your booze. That's something I don't know. But you can also use it for checking your antifreeze mix because the ethylene glycol and antifreeze has a different density than water. Don't remember if it's denser or less dense. Now, when a combination of units becomes complex and it gets used a lot, we give it a name. They tend to be named after famous people. So the Newton, that's a measurement of force. It's a kilogram meter per second squared. No one wants to write that every time. You write newtons. That's named after Isaac Newton. The joule, kilogram meter squared per second squared. That's named after Joule, who was one of the guys who figured out that heat was energy. He did a lot of early thermodynamics stuff. The watt, which is a measure of power. The joule is a measure of energy. The watt is a measure of power. It's kilogram meter squared per second cubed. You may have seen it on electrical devices, watts, named after James Watt, who vastly improved the steam engine and also invented the unit of the horsepower. So, for example, I saw a video recently that showed that a horse can put out 6 horsepower. The horsepower was a unit invented to sell steam engines. So it's a measurement of your average output of a horse over a day, not instantaneous output, which is why, you know, for 30 seconds or something, you have a horse output like 6 horsepower. And we're just about out of time, and that is where we wanted to stop. So I think we'll stop there. So, I have a sign-up sheet for the Getting to Know You meeting up here. Sign up for a slot. There's a set of slots available today, immediately after class today. You put your name here in the name column. Though I have other slots throughout the week. Over here. That's it. And there are more pages after that. Okay, I'll see you in a minute. Oh, yeah.